Hello and welcome back to CS422 Theory of Computation. And today we're going to start with chapter 1 after having motivated the study of computable decision problems as opposed to the undecidable ones such as the halting problem. So let me start the slides. Right, so Chapter 1 is about basic computability theory. In chapter 1, we will introduce first formal notions of computability as opposed to semi and decidability and enumerability. And we will proceed to compare these notions and their relations. Then we will see more examples of undecidable problems beyond the halting problems, and we will start to classify the undecidable problems by using a concept called reduction. Some of you may be familiar with polynomial time reduction, but without the qualifier polynomial time, that's actually historically the first notion of reduction, and that's what we're going to study and apply in order to formally compare problems. Then we'll have a look at the uncomputable functions as opposed to decision problems, namely at the so-called busy beaver function, or, which turns out closely related, the Rado function. Then we'll start to formalize what we actually mean by an algorithm. So up to this point, we can get away with our previous intuitive notion of what an algorithm is, but then we will start to formalize algorithm. And a particular feature of this course, CS422, is that we do not need to know about Turing machines. Everything we study turns out to be equivalent to Turing machines, but Turing machines are, I think, pedagogically very hard and distracting to get familiar with. So instead, we take the approach of considering so-called while programs and a variant so-called loop programs. And the distinction between while and loop programs turns out to correspond to something which is called the Ackermann function, which is good to know about independently of computability theory, for example, in discrete mathematics. So that's our plan, that's our schedule for chapter 1, and let's see how far we get in today's first lecture on basic computability theory. Right, so what does it mean to solve a computational problem? One of the strengths of computer science, with emphasis on science, as opposed to electrical engineering, is that we have formal definitions of concepts and therefore can prove that something is impossible, right? So in most engineering disciplines, the goal is to demonstrate, to construct something, to show that something is possible. But to show that something is impossible, that's really the strength of the sciences, and just to demonstrate how important and delicate that matter is. Remember that until easily 100 years ago, the common conception was that, for example, rockets cannot fly in outer space because in outer space there is no air against which the rocket can propulse against. But of course, nowadays we know that rockets in outer space are well feasible, going to the moon or Mars. And so this wrong proves saying that space rockets are impossible. This is because it was based on an engineering argument, whereas a formal proof that something is impossible, for example, in physics, there's no perpetuum mobile. This is really because physics is part of science. Okay, but back to computer science, to theory of computing. Here's our first formal definition. Well, to be fair, it's only half formal, but we'll get to there because it still involves the word algorithm put in quotes, because as you recall, we're going to formalize algorithm only later in chapter 1. So the emphasis in this part is the definition of what it means for an algorithm to compute a partial function. And here we consider partial functions from natural numbers to natural numbers, and we'll talk about partial functions with other domains and codomains in just a minute. So for now, let us restrict to functions that receive as argument natural numbers, that return as values natural numbers. And this symbol here we use to denote and emphasize that this is maybe a partial function. So it could well be undefined for certain arguments n. But definitely the domain of the function is allowed to be a proper subset of the set n of natural numbers. So here's the definition, and it consists of two conditions, two cases. The first case is when the algorithm is presented with an input that does belong to the domain of the function. And the second case is concerned with when the algorithm is presented with a natural number which does not belong to the domain of the function. So in both cases, however, the algorithm is presented with a natural number as input, as argument. And then it starts processing. And there are two possible cases. Either it terminates or it does not terminate. Remember, that was the essence of the halving problem. Now, if it does terminate, then the requirement says that it must print the value of that function on the argument x, which is another natural numbers. So here we're not yet precise about how to input and how to output, how to print a natural number for an algorithm. That comes later. But let's take for now that algorithm means your favorite programming language, C, Python, Java, whatever, where you know what it means to input an argument and to output or print a value. So for now, that should be good. The emphasis here is that for inputs, for arguments which do belong to the domain, the algorithm is required to terminate according to the definition. And prior to termination, right after termination, there's nothing to happen, right? But prior to that, the output, it must generate only one single output. It must print the value of that function, which is another natural number. So only one output must occur, and that output must be the value of the function, which is kind of intuitive and what we expect for an algorithm to compute such a function. The maybe less obvious part, and therefore important that we do take the effort of formalizing that, is what is the algorithm supposed to do when the input natural number does not belong to the domain of the function, that is, when the function is undefined on that input. In this case, our definition requires that the algorithm must not terminate. So that's a subtle point. In particular, we don't require the algorithm to say, in some sense, hey, this argument does not belong to the domain of the function. There's an error. That's not what we require. What we do require is that the computation must not terminate. And that's a subtle point, because recall that if a computation does not terminate, then the user running the computation on the computer can never be sure that the computation does not terminate. Could take an hour, could take a week, could take a year. And when the user maybe starts to get suspicious or runs out of patience and assumes that the computation does not terminate, then maybe just a minute later it does terminate. So a user can never be sure about a non-terminating computation. Whereas when the computation spells out an error message, hey, argument does not belong to the domain, this is undefined, then of course the user would know, but this is not what we require. We require the weaker condition. And the reason for that will become apparent later throughout this course. Okay, but for now, the important thing is that we have formalized something which previously may have been ambiguous, which we had asked different people on the street, could have given different answers, but now we're all on the same page, as one of the virtues of computer science, fully always precisely specify what we're talking about. And here we're talking about what it means to compute a partial function. Good. Another concept, another notion that we're introducing here on this slide is what it means to decide a subset of natural numbers. Okay, deciding a subset, intuitively the difference between computing a function and deciding a subset is that the result, the output of a function computation can be any natural number, whereas the output, the result of a decision, can be only yes or no, or for simplicity, since we're only talking about natural numbers, only the natural numbers 0 and 1 are permitted outputs in this case. Okay, so in particular, deciding is a special case of computing, namely the case where the output is only 0 and 1, depending on the value of the characteristic function. So I recall that the characteristic function of a subset L of natural numbers has the value 1 on arguments that do belong to the set L, and has the value 0 on arguments that do not belong to the set L. So this kind of captures really the essence of deciding something where the answer is only 0 or 1. And whether the answer is 0 or 1 is here mathematically represented and coded in terms of this set, whether the argument does belong to the set or does not belong to the set. So that's the core here. And we have some more notions that may not be as intuitive, right? So one thing to emphasize already here is that the characteristic function is a total function, right? Characteristic function is always defined. Its value is either 0 or 1, but there's no such thing as undefined for a characteristic function. Therefore, and recall that here we define deciding in terms of computing, and computing is defined here, but we define it in such a way that the second case does not occur because the characteristic function is always defined. So the case where the argument does not belong to the domain of the characteristic function does not occur. In particular, the user running a decision algorithm will always get an answer and will be able to be sure of the answer. So the case where the user is not sure because the computation does not terminate does not occur according to this notion. So this is a strong notion intuitively. What is a weaker notion? A weaker notion is semi-deciding. So the notion is already, the terminology is already chosen carefully, such as to be weaker, namely only half of deciding. Semi meaning half. Okay, and here the condition is that an algorithm semi-decides a subset of natural numbers if the algorithm terminates precisely on those inputs that belong to the set. Or put differently, it does not terminate, it runs forever on inputs which do not belong to the set. So recall that when the algorithm runs forever, which here means that the argument does not belong to the set, then the user can never be sure. So semi-deciding in this sense is a weak notion, in that in half of the cases, the user does not really get an answer, or at least cannot be sure of the answer, because the computation takes forever. Whereas in the other case, when the computation does terminate, then the user knows and can be sure that the computation indeed has terminated, then the argument belongs to L, because then, yeah, that's a sense of a terminating computation. When it does terminate, the user gets a feedback like computation terminated, or prompt appears, or whatever. So that's kind of a, yes, therefore a weaker notion. And we will justify that notion in just a minute, and in particular, justify why it is, in a sense, half of deciding, semi-half. But before that, let us also pop up the final notion, which is called enumerating a set. Enumerating corresponds to, right, so in the previous cases of deciding and semi-deciding always involve some input, right? And the computation, sorry, revealing some property of the input, either 0, 1 in the decision case, or terminate as opposed to not terminating in the second case. Enumerating, on the other hand, is a notion which involves only output, namely computing a total injective function, which we have defined before. And the emphasis here is now that this is a total function, right? And to see this or to motivate this, suppose you have a list of all possible words in your favorite language, let's say English, like a Oxford dictionary, right? Which contains all valid words in the English language. And so now if somebody tells you a word like flabbergast, where you're not sure whether that is a valid word in the English language or not, then a decision procedure, if you have a decision procedure, you could enter that word into the decision procedure and it would tell you, yes, this is an English word, whereas another word I'm going to make up is not an English word. The semi-decision procedure would in this case terminate, whereas on another input, which is not an English word, like kraut, this semi-decision procedure would not terminate on the word kraut, but would terminate on the word flabbergast. Okay, so remember that based on this semi-decision procedure, you cannot be sure ever that kraut is not an English word. And in the final case of enumerating, that would be an algorithm that just prints out the entire Oxford dictionary, only output, output, output. And then it is up to you to look up whether in this output the word flabbergast appears. But there's a caveat, namely the order of the output is arbitrary. That is, unlike the Oxford English Dictionary, where the words appear in lexicographical order, here the notion just requires to output all and only the words of English language in arbitrary order, which seems not very helpful, but we'll get to that. Namely, we'll specifically compare these three notions in a few minutes. But first, let's look at the formal definition of what it means to enumerate. Namely, it means to compute some total injective function whose range, that is the set of values, coincides with the set L. Or differently, spelled out more explicitly, every word in L must occur and no other words must occur in the output, and the output here being formalized and represented by a total function. So I mentioned f of 0 to output 1 word of the Oxford English Dictionary, any, not the first one, just any. F of 1 outputting another one, F of 2 another one. So by repeatedly running that computation on 0, on 1, on 2, 3, and so on, that computation indeed eventually outputs the entire English dictionary, but let me emphasize that, I cannot emphasize that enough, in arbitrary order, not in the order yet you might prefer, lexicographic or anti-lexicographic or anything. It's really entirely up to the algorithm according to this definition. And it must be a total function. Okay, so there's a very good question in the chat. Thank you very much. Namely, we use here a lot of mathematical terminology. And one thing I'd like to emphasize is that with natural numbers, being the computer scientist that we are, we mean the set of non-negative integers. In particular, 0 is, to us, is a natural number. So when I say f of 0, that's really the very first element, 0, 1, 2, 3, and so on. 0 is a natural number. That's the first good question that I'm happy to use the opportunity to clarify here. Second question in the chat is about what it means precisely. Yes, so this word is here underlined for good reasons, because indeed, as suggested in the chat question, it means it terminates on inputs that belong to L, but must not terminate on inputs that do not belong to L. On inputs that do not belong to L, it must not terminate. So here really another case of the definition requiring non-termination, namely non-termination for inputs that are outside of the language L. It's often called language because of its history in the theory of formal language theory, like with Chomsky. But for our purposes, it just suffices to consider L as a subset of natural numbers including 0. So thank you for this question and for the opportunity to clarify this, because most likely not just you who put up the question, but somebody else also might have the same question, and is grateful that you made me explain that more closely. Okay, so now we have formalized 4 notions. 3 of them refer to decision problems, to a subset of natural numbers, where basically the output of the any query, any natural number is kind of a query, and the reply, the output, in this case must be mathematically is a Boolean. Yes, belongs to L, no, does not belong to L, but the subtlety here for computational purposes, we also consider cases where the computation is not required and actually is prohibited from providing any answer, namely in this case when X does not belong to L. And the more general notion of computing has also such a required non-termination. And in addition to that, it has outputs that may exceed the Boolean value 0, 1, true, false, yes or no. Now, what if we want to study or even define computation on sets other than the natural numbers? Observe that all the problems we consider here have natural numbers as inputs. Nothing else can be even input according to the definition. Not a binary string, no executable, nothing. Is that a restriction? Is that serious for our notions, for our concepts, for the rest of this lecture? If we want to say, compute some problem involving graphs. It turns out that it is not, and the technique basically to achieve that combines several natural numbers into one single natural number. combine several natural numbers in a single natural number in such a way that the computer can recover, kind of undo the computation process. Put differently, if the user wants to perform some computation that involves several natural numbers, maybe a vector of natural numbers, maybe even a matrix of natural numbers, then the user can apply, is required to apply that pairing function, which we'll talk about in a minute, in order to combine all these numbers into one single natural number, feed that into the computation, and the computation, by the very construction, I'll say that or in a minute, is able to then decode and decompress and decombine from that single natural number input all its parts that it had consisted on initially. So our computation, or definition of computation, does not allow for the input of several natural numbers, but instead our definition in such a way that the user combines several natural numbers into one single, inputs that to the computation, and the computation can then recover from that the individual natural numbers. Okay, and that function that combines several natural numbers to a single one in such a way that it is possible to recover the single natural numbers, the individual ones. That, of course, requires the function to be injective, right? To be one-on-one. Because if several natural numbers get mapped into the same one, then it's not even information theoretically, not even mathematically possible to recover the original natural number, because it's not clear which ones were meant in the first place. So to many students, this initially comes as a surprise that this is possible. So let's look more closely at that. And such a function, such a pairing function is sometimes also known as Hilbert Hotel, which I'll tell about an anecdote in a minute. So here's the function. It receives two natural numbers. It only involves an arithmetic, that is addition and multiplication. Here's some constant. And this division by 2 is actually not a division by 2, because you can see precisely one of these two factors here is going to be even, depending on whether x and y are even, but precisely one of them is going to be even, and therefore the product of both is always going to be even, so we can divide it by 2 and obtain a natural number, not a fraction. So this is really well defined, a function that takes a pair of natural numbers and returns as value a single natural number that combines the two numbers. And I'll leave it to you, maybe in a homework, to verify that this is indeed an injective function. So put differently, if x comma y combined equals x prime comma y prime combined, then x must be equal to x prime and y must be equal to y prime. That's the very definition of injective, right? Moreover, it is computationally not very hard to compute the function, nor to compute its inverse, the inverse that allows to recover the initially encoded numbers, because the coding part only involves arithmetic, as we discussed, and the decoding part, to be fair, superficially seems to include some square root, because there's a multiplication to be reverted, but we can replace the square root by some searching, because then remember that x and y are natural numbers, and therefore one can basically simply try, when we're given the value of the pairing function, one can essentially try which x and y paired produce that value. So that being said, the proof that this function is injective, that's not our focus. That's a nice homework assignment, for example, in discrete math. This is just one example of an injective pairing function that takes pairs of integers and produces an integer in an injective way. There are many other examples, but we're going to stick with this one also for convenience and for complexity purpose. But complexity, recall, that's entirely different topic that's will occupy us throughout the second half of this course. Now, why is this called the Hilbert Hotel? There's this anecdote. Hilbert, David Hilbert, rumors say, run a hotel with a countably infinite number of rooms for guests. Let me say it again. Hilbert's Hotel, which is only a thought experiment, provides a countably infinite number of rooms. And now let's suppose that these rooms are all occupied with guests, with visitors, but it's evening and one more visitor arrives. What will the reception at this Hilbert Hotel do? Well, the reception, being a mathematician during the low business times, asks every single guest in the hotel to move from room n to room number n+1. Let me say it again. The clerk of the hotel, with countably infinitely many rooms which are all occupied, rooms which have numbers numbered from 0 to 1 to 2 to 3, starting with 0 because we're computer scientists, will ask every single guest being in his or her room to move to the next larger room, the room with the next larger room number, from room n to room n+1. And notice that room n+1 is indeed available because the guest in room n+1 is moving to room n+2. So every single room, every single move is indeed feasible without having a double occupancy. Well, many people might meet on the floor during the move, but after the move, everybody will be back into an individual room that contains nobody else, except for the room number 0. The room number 0 was initially occupied, but the person in room number 0, remember, moved on to the room number 1, which became empty as the person in room number 1 moved to the room number 2. So that in the end, room number 0 will be empty. And that's where the new additional late guest can move in happily ever after. Well, that's not the entire story of Hilbert Hotel, because the next evening, it's not just one guest arriving in the already occupied hotel, but it's a bus, a huge bus, a bus as huge as to have a countably infinite number of guests. So Hilbert's Hotel has countably infinitely many guests, but it's fully occupied. And now a bus comes, which also has countably infinitely many guests. How can the clerk of Hilbert Hotel accommodate all these new guests? Well, the clerk will modify the original strategy and now ask every guest in room number n not to move to room number n+1, but to move to room number 2n, twice the original room number. And again, observe that room number 2n is indeed available because the guest in room number 2n will move to room number 4n, and so on. So that this is really a well-defined move. And after this move, every guest will again have an individual room by him or herself. But after this move, all the rooms with odd numbers have become available. All the rooms, the guests in rooms with an odd number like 3, have moved to room number 6. The guest in room number 5 has moved to room number 10. So that the room with an odd number is empty and remains empty because nobody moves into such a room with an odd number. That's the whole point of an odd number being not of the form 2n, where all the guests have moved to. So that after this kind of move, again moving everybody in the hotel, but now all the rooms with an odd number have become empty and available. And there are, of course, infinitely many odd numbers, 1, 3, 5, 7, 9, and so on. And this is where now the bus with the infinitely many new guests can move in, right? Because countably infinitely many guests can fit into the countably infinitely many odd natural numbers. But this is still not the end of the story. We haven't really used the pairing function yet. In order to use the pairing function, the next night in Hilbert's hotel, which is again and still fully occupied, good business, right? But now it's not just one bus with an countably infinite number of guests arriving, but it's actually countably infinitely many buses. Yes, the hotel has a huge parking lot. So it's countably infinitely many buses that are arriving, and each of these buses are fully occupied, as is the hotel. No, let's make things more simple. Let's say initially the whole hotel is empty. So we just need to deal with the buses and not with the existing occupants. So still we have this countably infinitely many buses, all fully occupied. How can we fit them into the hotel? And this is where the pairing function comes into account. Namely, the pairing function, we apply that with x being the number of the bus we're considering. So we look at one bus, let's say the bus number x, and in bus number x, we look at the passenger number y. Since this is countably infinitely many, it means that every bus and every passenger in any bus can be described by a natural number. First one by a natural number called x, second by a natural number called y. And now we plug these natural numbers x and y into this pairing function according to this expression. Don't worry too much about the expression. The result being again a natural number, and this is the number of the room we're going to put the visitor number y from bus number x in. So that by means of this assignment of buses and guests to rooms, in the end, every guest has a room. That's true because that's a natural number. But the interesting thing is, none of the rooms will be occupied doubly. There will be no collision because this is an injective function. Any collision would mean a violation of the injectivity. So that's the essence of Hilbert's hotel and the pairing function, that it kind of describes a way of fitting countably infinitely many buses with countably infinitely many guests in each into one Hilbert hotel having only once countably infinitely many rooms. So that's the story behind Hilbert's hotel and the pairing function. And now having said that, we can move on. And who is there? Question, let me check. Right. Yes, you're welcome and encouraged to take notes during the lecture. And the lecture will be made available via video and as PDF and as a PowerPoint source. Thanks for that question. Yes, indeed. That's a great idea to take notes during the lecture. Okay, now moving on. How do all these notions relate to each other? Right, the notion of computing Well, that's only a notion that applies to functions. But regarding decision problems, we have now three different notions: deciding, semi-deciding, and enumerating. And that naturally raises the question, is there some connection, some relation between these notions or not? And if there is a connection, what is that connection? And the answer to that is provided by the following theorem. Well, the theorem comes in a minute, but first let's look at an example, namely the halting problem. We now can formalize finally the halting problem. Previously, we said the halting problem is a question about a pair, algorithm, and input. But our definition doesn't really speak about questions. It uses mathematical concept, subset of natural numbers. How can we formulate and formalize the question halting problem as a subset of natural numbers? And we do that by saying that we recall that we have a pair, algorithm, and input to the algorithm. That's the question whether the algorithm on that input terminates or not. And the pair, algorithm, and the algorithm, we call that any algorithm, can be expressed as a natural number. How is that possible? Well, any algorithm can be written down as a finite sequence of, let's say, bits. Well, let's take that sequence of bits and interpret it as the binary representation of natural number. Thus, every algorithm is a natural number. Not conversely. There are many natural numbers that do not correspond to algorithms. They might correspond to some source code which lacks a syntax, exhibits a syntax error, for example. But the baseline is that every algorithm can be encoded as a natural number. And so can the input to the algorithm. And the pair algorithm, input to the algorithm combined constitutes again a natural number using the Hilbert total pairing function. And we can thus formalize and define mathematically the halting problem as a subset of natural numbers, namely the subset of all encodings of pairs of algorithm, input to the algorithm as a natural numbers that terminate. Whereas those which do not terminate are by very definition not an element of this subset of natural numbers. And those that are not encodings of a syntactically correct algorithm are also not element of that formalization of the halting problem as a set of natural numbers. So now we can indeed move from the informal conception of a problem as being a question to the more formal notion of a problem, decision problem, being a subset of natural numbers. And again, the emphasis on natural numbers, because what if we want to talk about other sets of inputs that are not natural numbers, then we can encode them as natural numbers. And I'll say more about that in a minute, but let's first state the theorem, which exhibits all the relations, the logical relations, mathematical connections between these three different notions. Okay, so and the first part of the theorem states that deciding finite decision problems is kind of trivial in the sense that every finite set is decidable. Okay, let's postpone the proof for a minute, but let's just first really savor and digest the statement. Every finite decision problem, here remember decision problem, is decidable. Okay. Meaning that the interesting decision problems, those which we will investigate further in the rest of this lecture, are going to be the infinite one. There's no point in really considering the finite case, because there everything is decidable. That's the first claim of the theorem. The second claim of the theorem is about some closure property. The closure property says that subset L of natural numbers is decidable if and only if its complement, the set of natural numbers which do not belong to the set, is decidable. And again, the simple proof will follow in just a minute. But first, let's again digest the meaning, the intuition of this statement, namely that the set of decidable, the hyperset of decidable sets, is closed under complement, closure properties. That's something nice. It will seem in a minute that this is not always the case, namely for the weaker notion, a set L is decidable, strong sense, if and only if, recall that first, if and only if both the set and its complement are both semi-decidable. So what I try to emphasize here is that this item C kind of justifies our terminology. Why do we call set semi-decidable in this sense? Because semi-decidable is really half of being decidable. The first half here and the second half kind of in the complement. That's the same as being fully decidable. Seems intuitively clear and justifies the terminology, but the proof is not difficult. It's something we'll get to in just a few minutes. But first, the final statement of the theorem that, so now we've related semi-decidability to decidability, and now we're going to relate enumerability. Maybe we're going to relate enumerability to semi-decidability, not to decidability, because the relation to semi-decidability is much simpler to state. And we're proving that in just a few minutes. Namely, the relation is enumerable is the same as infinite and semi-decidable. So now recall that according to item A of the theorem, the finite decision problems are trivial, decidable. So it's no restriction for item D to really restrict to infinite decision problems. And for those, enumerable is actually the same as semi-decidable. Right? That's a statement, and that really tells us already a lot about these formal notions of computability. Namely, we don't need a new notion of enumerability. In the sequel, as in many textbooks, these are used synonymously with semi-decidable, which is justified by item D, because the finite case is trivial by item A. So if you read a textbook and you see enumerable, and different textbook you see semi-decidable, most likely they mean really the same thing, subject to whether decision problems that are finite are even considered or discarded, as we are doing. Okay, so big achievement here, having formalized, identified, it's important, identified, formalized, and then put into relation all these three notions. So what we now do is to prove the theorem, right? Remember, that's the essence of computer science, with emphasis on science, that we can prove something, and here that's what we're going to do. And in order to prove that the set is decidable, the finite set, what does it mean to be decidable? It means that there's some algorithm. We're at this moment still at the intuitive conception of an algorithm. Some algorithm that decides this set L. Now, the hypothesis we have about the set L is that it is finite. So there are finitely many natural numbers. And we're asked to devise an algorithm. Our algorithm that we devise contains this finite list of these natural numbers, encoded in binary or whatever, in your favorite programming language, you can introduce some constants, right? So in Pascal, it's really explicitly expressed as const. In BASIC, it's like data. In Java, it's a variable with initializer. In Python, anyway, every programming language has a way of using constants whose value is hard-coded in the source code. You need to change the source code in order to change the value of that constant, as opposed to numbers that are input, that are requested to be input. So now how can we use that in order to design a decision algorithm? Well, our algorithm has this finite list, emphasis on finite, because we can only encode finitely many natural numbers. Infinitely many natural numbers, that would be very long source code, right? No, I'm kidding. That would be infinitely long source code, which is not a source code at all. But since the hypothesis is that L is finite, we can enumerate, list, write down all the elements of L, which are natural numbers, and we can write them down in the source code as a constant assignment or a list or data. And using that, we can then append an algorithm that uses this constant data in order to check for a given input whether that input coincides with any of these finitely many data, finitely many integers. It's using just some loop, for example, of constant size. Remember that the set L is fixed. It's finite. It can be very large, but it's finite and it's fixed. And therefore, in principle, it can be hard-coded into the source code. And then the source code receives its only input. This is not input, but the source code receives an input and a natural number. Let's call it X. And then has to check whether X belongs to L or not. And the algorithm can do that by walking through that initialized data that contains all the finitely many elements of L to see whether the input is equal, coincides with any of these inputs or not. And if it does, then the algorithm can output yes or true or 1. And if it does not, if the search exceeds the range of the constant data, then let's say we design the algorithm right to say no, to say 0, to say not element. And recall that we are currently designing the algorithm because that's kind of our job in order to prove that this set is decidable, which we've done, and thus complete item A. Now let's move on to item B, which is an equivalence, if and only if. So what we're going to do is we're going to prove two directions. We're going to prove that if L is decidable, then also its complement is decidable. And then we're going to prove the converse direction, but one step at a time. So let's suppose that L is decidable. And we need to prove that its complement is also decidable. So recall what it means to be decidable. It means there exists an algorithm which computes a characteristic function, a total function. Total function meaning, if we consider the complement of the characteristic function, that is 1 minus the characteristic function, then this will be a solution to the complement of L. It will output 1 whenever the argument does not belong to L, belongs to L prime, L bar, and will output 0 if the argument does belong to L bar, it does not belong to L bar. So how can we turn that algorithm that we've just analyzed and saw that it behaves in a certain way? How can we turn that into an algorithm that decides the complement? And I emphasize that we're here turning that into the algorithm using the hypothesis that there's an algorithm for this. Whereas in the first case, we just started to devise an algorithm from scratch. So how do we do that here? We look at the existing algorithm, which we know to exist, since by hypothesis, this is decidable. That's all we know about the algorithm. And now we're going to modify that algorithm. Whenever that algorithm outputs yes or 1, then we're going to, our new algorithm is going to output no or 0. And vice versa. Whenever the algorithm is going to output no or 0, then our modification, the way we modify it, by switching all trues to false and vice versa, then our algorithm will output yes. So that this new algorithm indeed decides precisely the complement, which I'll leave it to you to double check. And for this again, what does it mean to decide? To output yes for inputs that belong now to the complement, output 0 for inputs that do belong to the complement, and never output I don't know or anything, because that case is not allowed here. Yes, moving on to the third item, which is the justification of semi-decidability. For the by the way, the converse direction of item B, we don't need to prove, right? Because the converse direction, if L complement is decidable, then also L is decidable, just follows from simple Boolean argument. Because if the complement is semi-decidable, then since item B applies to everything, that means also that the double complement is semi-decidable, but we know that the double complement is just the original set. So that problem went away easily. The next item is a little bit more challenging and more work, so let's look at that. So the hypothesis that we use here is that L is decidable. Let's look at that direction first. So L is decidable, so there must exist some algorithm. We don't know anything about the algorithm except that this algorithm always terminates because L is decidable. Remember here. And the algorithm only outputs 0 or 1, true or false, yes or no. And now we need to convert that into two algorithms. We know there exists one algorithm here, and we need to show that there exist two algorithms with a certain behavior. And these two algorithms are going to be as follows. So the first algorithm that semi-decides L will simply execute the algorithm that decides L. And when that algorithm is about to produce its output, remember it always produces either 1 or 0 and then terminates. Whenever it produces the output 1, then our new algorithm will simply terminate. So we're doing again this game of taking a hypothetical algorithm and then applying some modification to the hypothetical algorithm without requiring any knowledge of how this hypothetical algorithm would proceed. That's the same how we proved that the halting problem was undecidable. We took a hypothetical algorithm B purportedly claiming to decide the halting problem, and then we've modified it in such a way to arrive at the contradiction. That's what we do here, except here we don't want to arrive at the contradiction, but we want to arrive at an algorithm that semi-decides the set L, for which case it must terminate for inputs that belong to L. That's already something we had in the first case. But it must not terminate on inputs that pertain to the second case. It must not terminate when the input it receives does not belong to the set. That's a difference. The original algorithm does also terminate in this case, and output 0. The new algorithm must not terminate. How can we find this new algorithm? Well, here's one way. whenever the algorithm that decides and therefore always terminates the set L, whenever that is about to output 0, which happens at least once, maybe several times in the source code, then we change that. We replace that command, however it looks, to output 0 by a different command that simply deliberately goes into an infinite loop. And that's it. Because now this algorithm terminates precisely on inputs that belong to L. For inputs that belong to L, the algorithm computing the characteristic function will terminate, simply terminate and not output 1 because we've applied the first modification. Whereas for inputs that do not belong to L, our new algorithm will instead, when simulating the given algorithm, run into this case, and before and instead of outputting 0, our algorithm will, remember the way we've modified it, deliberately enter an infinite loop. So that demonstrates and concludes one direction in item C. If L is decidable, then both L and L's complement are semi-decidable. Well, technically, we've only proven one part. We've proven if L is decidable, then L is semi-decidable, which already almost justifies the terminology semi-decidable. But how about the second case? When L is decidable, then L's complement is semi-decidable? Yes, it is because of item B. According to item B, if L is decidable, then also L's complement is decidable. That's what item B says. And now apply the part of item C that we've just proven. Since the complement of item C is now known to be computable, then the part of the claim that we have already proven finally yields the claim that we're still had been missing, and we're done. So this is an example of kind of how to say efficiency in proving theorems, trying to do as little proofs as actually necessary, and then deriving the remaining arguments from the given proofs. You can also give a proof directly that if L is decidable, then L bar is semi-decidable. That's maybe a great thinking about a great exercise, great homework assignment. But this is only one direction of this claim. Now let's look at the converse direction, where the hypothesis is that both L and L's complement are semi-decidable, which means that there must exist two algorithms, one that semi-decides L, let's call that algorithm A, and another algorithm that semi-decides L's complement, let's call that algorithm B. How can we combine these two algorithms that only semi-decide and in particular may fail to terminate? How can we turn that into an algorithm that always terminates, because that's a requirement for being decidable? And furthermore, an algorithm that actually decides the set. So here's the first idea. First idea is to simulate the first algorithm A on the given input. If the algorithm A eventually terminates, then we know that the input belongs to the set L, and we can safely terminate our computation of L, which uses that hypothetical algorithm A. But if the hypothetical algorithm A does not terminate, because the input does not belong to X, it must not terminate, then we might try to execute the second algorithm B, which semi-decides L prime, and proceed in this very same way. If the algorithm semi-deciding L prime terminates, then our master program will answer no, will answer 0, because our master algorithm is supposed to decide. But we never get to that case, right? So we never get to the algorithm B in case the first algorithm A never terminates. It never terminates because we're talking about the case where the input does not belong to the set. So that's not going to work. What else is going to work? Let's try it the other way. Let's try our algorithm to decide L by first running the algorithm that semi-decides L bar, and then running the algorithm that semi-decides L. But that does not work either, right? Because the algorithm semi-deciding L bar, if the input does belong to the set, then that algorithm must not terminate. Let me say it again. The algorithm semi-deciding L bar, the complement of L by the very definition, must terminate precisely on those inputs that do not belong to L. So when we present that algorithm with the input that does belong to L, it will never terminate. And in particular, it will never get around to the other phase of our algorithm purportedly deciding. But our new algorithm must always terminate. So there's now some idea required. And that idea is sometimes called dovetailing. So we cannot first run the algorithm A semi-deciding L and then algorithm B, nor can we first run the algorithm B semi-deciding L complement and then the algorithm A semi-deciding L. Instead, what we're going to do is we're going to simulate both simultaneously, or if you have a single processor machine model in your head, instead of simulating both simultaneously, we're going to have our simulator simulate one step of the first, one step of the second, second step of the first, second step of the second, and so on, like Hilbert's hotel after it had been received 2 infinite buses. So simulate one step from the algorithm semi-deciding L, then simulate one step from the algorithm semi-deciding the complement, then simulate the second step here, simulate the second step here, always, of course, keeping the memories and everything separate so that the two simulations, which are now running pseudo concurrently, that these two computations do not interfere and affect each other. Pseudo concurrently, because that's actually what your computer does when it seemingly is running several programs simultaneously, as is nowadays standard. Because running programs concurrently, actually in physical hardware, what happens is that the computer is switching back and forth between several programs in ways that is such fast that nobody hopefully really realizes that all this switching is going on. And now with this alternating computation, one step here, one step here, this is easy to, combine it to one algorithm. And then this algorithm, you can see, indeed decides the set. Why does it decide? Well, let's analyze this algorithm on some given input X. And remember that the algorithm will alternatingly simulate one step of the algorithm semi-deciding this, one step semi-deciding this, one step semi-deciding this, and so on. And precisely one of the two simulations will terminate. Let me say it again. If the input X belongs to L, then the first computation terminates. If the input does not belong to L, then the second computation terminates, right? So precisely one of the two computations that are now executed carefully, alternatingly, precisely one of them will terminate and succeed. And which one tells us whether the input belongs to L or does not? If the first one succeeds, then the input does and must belong to L. If the second one succeeds, then the input does and must belong to L complement, that is, must not belong to L. And our meta algorithm that keeps simulating alternatingly can detect which of the two cases happen Eventually, there's no bound on how long it takes to keep alternatingly simulating. One step here, one step here, one step here, one step here, until one of the two terminate. It can take very, very long time, but eventually one of them will terminate, and then our algorithm can act and report accordingly. Output 1 in case the first simulation was the one to terminate, and output 0 in case the second simulation was the one to terminate. But the message here to take from here is we really need to modify the algorithms that were only guaranteed to exist according to the hypothesis, and then modify them to obtain an algorithm with a required and desired property. Okay, so then we're already almost done. What only remains is to prove this equivalence, and that's going to be the final proof of this lecture. Then we're going to briefly recap and we'll be done. Thanks for staying on, for paying attention. Just the final proof of this equivalence. So let's look at one direction first. Suppose L is enumerable. That means, by the very definition, that there exists this algorithm that enumerates such a function, some total injective function whose range, whose values coincide with the set L. Now observe that this function is required to be total and injective with the infinite domain, and therefore also the codomain, the range must be infinite. Injective function, total domain must be infinite. So this condition is already satisfied by injectivity. And how can we prove it semi-decidable? To this end, we again apply this our technology of modifying the algorithm without knowing anything about the algorithm other than it exists, the algorithm enumerating L. Namely, we're going to modify that algorithm so that the new algorithm, let's call the original algorithm A, and our new algorithm B. Our new algorithm B, remember, will receive some input natural number, let's call that X, whereas the algorithm enumerating only computes this function and or predictably outputs the entire dictionary. So our new algorithm B receives as input some natural number, and it will then run and simulate the algorithm A on input 0, that is thus recovering the first natural number enumerated by this algorithm. And then it will do the same again with the second, with the third, and so on with every single natural number, and each time receive a different natural number here as output. And our algorithm B compares that output to its own input X. So here I'm describing in words, without pseudocode, some algorithm, and claim that this algorithm semi-decides L. Why does it semi-decide L? How does it behave? If the given argument X belongs to L, then by the hypothesis of enumerating, that means that the other algorithm A will output that X at some point on some argument to F. And our algorithm B that simulates and executes that algorithm on every possible argument will eventually run into that argument and will thus produce the output that coincides with X, and our algorithm will thus terminate. First case. Second case, our algorithm B receives as argument at X, which does not belong to L. In this case, it will keep simulating algorithm A on all possible arguments 0, 1, 2, 3, and thus produce many different values, but none of them will coincide with X because we're just talking about the case where X does not belong to the range of the function. which means that our algorithm B will continue to simulate, and search for an argument that makes F value coincide with X, but it never happens. In particular, it will continue running forever, which is precisely the condition of semi-deciding. Our algorithm B thus terminates on arguments X that belongs to L and does not terminate on arguments that do not belong to L. Thus, we have proven one direction. If L is enumerable, then it is infinite and it is semi-decidable. The very final thing for today is the converse. So stay tuned. It's only going to be 3 more minutes. So now we suppose that the set L is infinite and semi-decidable. That is, there is some algorithm with this behavior, algorithm that terminates precisely on inputs that belong to L. Recall that this algorithm requires some input. And the claim is that in this case, L is enumerable, meaning that there exists such a function which computes a total injective function. And we're going to design and describe the algorithm that performs this computation using the algorithm for semi-deciding. So how does that work? Our new algorithm will take a first argument n equals 0 and check, run the computation, and yeah, I think we should take more time for that. Let's postpone that until the next time, and let's close by having a recap and answer some questions. So what we've started in this chapter 1 is with introducing formal notions of computation, of computability. And the 4 notions we've introduced is computing a partial function, deciding a subset of natural numbers, semi-deciding a subset of natural numbers, and enumerating a subset of natural numbers. That's a very important first step. First, establish formal notions. And then we have started investigating the relations among these notions. And the relations are captured by this theorem. First, decidability is closed under complement. Secondly, semi-decidability is indeed half of decidability in this sense. And third, enumerability is almost the same as semi-decidability, except for this condition that a set under consideration must be infinite, because if it's not infinite, if it's finite, then this is a trivial case which we are not really interested in, which we thus can ignore and not talk about any further. And the proof of these statements involves interesting techniques which will be of relevance later. Simulation techniques. Suppose the hypothesis just guarantees that there exists an algorithm and says nothing more about this algorithm. And our proof takes that algorithm, modifies it, and turns it into another algorithm with a different behavior, a behavior as claimed, as purported, according to the statement. That's one proof technique, taking an algorithm, modifying it. Another proof technique is simulating an algorithm step by step, and more generally simulating 2 algorithms, alternating these step by step to see which one terminates first, provided that we have a guarantee that at least one, or precisely one of them, terminated. And this is better than first simulating the first algorithm through, because that may never terminate, may never reach the second algorithm. So simulation and alternating the simulation, this is called dovetailing. Good, that's a recap of today's content, and I'm happy to answer final, again, excellent question in the chat. Namely, are there examples of problems which are not semi-decidable? We've seen that the halting problem is not decidable, but how about something that is not semi-decidable? And that's an excellent question, and I want to leave that as a cliffhanger to the next lecture. So thank you very much for asking that question. We'll answer it next time. Thanks everybody for joining. Thanks for your attention, and see you next time.